good morning to everybody here in New Mexico and everybody west of the Mississippi. Good afternoon to everybody on the East Coast and good evening to those that are across the pond. Thank you so much for joining us today. So we have Thomas Kruijer here with us from Lawrence Livermore National Laboratory. And so Thomas is a staff scientist in the Cosmic Chemical and Isotopic Signature Group at LLNL. Thomas received his PhD from ETH Zurich, Switzerland in 2013, specializing in isotope, geo, and cosmochemistry. His research is focused on determining the origin, accretion, and early evolution of protoplanets, the terrestrial planets, and the moon, as well on addressing problems in nuclear forensics. This is accomplished by reconstructing the processes and events using isotopic signatures and chronometric tools. To this end, Thomas measures small-scale isotopic variations in meteorites, lunar rocks, and anthropogenic samples by utilizing novel and precise isotope ratio mass spectrometry techniques. And so, Thomas, we are so excited to listen to this talk, and so please tell us about the high-resolution chronology for crustal magmatism on the moon.
All right, yeah, well, thanks a lot for the nice introduction, and also thanks a lot for inviting me to give this talk here today. So it's the day after the election, so no better time than to discuss the chronology of lunar crustal rocks, I suppose. So I would like to just give you essentially a bit of a status update on the chronology that we've been doing here at Lawrence Livermore National Lab. And most of this work is done here at the lab, but we do some aspects in collaboration also with UCLA. Ming Chang has used the SIMS facility there. And also in collaboration with the University of New Mexico. So I would like to start off showing you an image, actually not of the moon, but of the Grand Canyon, to lift everyone's spirits. And this is very much, of course, one of the hallmarks of terrestrial geology. And it's a beautiful image showing you stratigraphy that basically shows you billions of years, billions of years of geologic history on Earth. And what we have on Earth, of course, is a very nice stratigraphy of rocks that provides some order that can be used to interpret the geologic history. Now, if we go to the moon, and this is an image of that was taken during Apollo 17, the field relationships that we find there are much less clear. And this is basically how it looks like. A lot of the moon's surface is covered by a regolith layer. And occasionally you find boulders like these that you can do some field geology on. So there's less of a framework into which to interpret the geology of this body. So in that sense, it is very useful to have some other framework, and this can be provided by the chronology of lunar rocks. And this has been very helpful, amongst other things, to interpret the early evolution of the moon. And this is basically our type of work that we do here at Lawrence Livermore. And what we specifically do is we want to reconstruct the sequence of magmatic events in order to determine the moon's igneous differentiation history. However, there is one major challenge that I would like to pose here, and that is that a lot of this igneous record on the moon is somewhat perturbed by the record of large impacts onto the lunar surface. And this makes interpreting these events somewhat difficult. And to do this accurately, we require very careful sample selection of Apollo samples, of lunar meteorite samples, alongside adequate analytical techniques and precise age determinations on lunar rocks. Now, to kind of set the stage and get everyone on the same page, I would like to very briefly go to the general evolution of the early moon. And as most of you know, the most widely accepted model for the formation of the moon is a giant impact kind of happening on the proto-Earth, and the debris of that impact may be the material from which the moon then accreted. And at that point, the moon was very hot, likely very molten to a large extent, and then it started to cool down. And in this cooling history, various mineral phases started to crystallize, and this is known as basically the lunar magma ocean model. This started with the crystallization of mafic minerals, forming mafic cumulate layers in the lunar mantle, as well as the crystallization of plagioclase that then floated to the surface of this magma ocean to form an anorthositic crust. And the residual liquid of this magma ocean is thought to have been a component known as ore-creep, which is enriched in incompatible elements and rare earth elements. Now, we also know that there were likely several secondary pulses of magma that caused secondary magmatism into the lunar crust. And I will talk a lot about that today. And all of this was then kind of overprinted by a prolonged history of impact bombardment on the lunar surface. And that is essentially the challenge that I presented in the last slide. Now, today I would like to discuss the lunar crust kind of in some detail. So I would like to give you just a very brief overview of the lunar crust as we know it from the Apollo missions. The main crustal rock suite that we know is known as the Verona Northocide suite. This is essentially primordial crust, this flotation cumulate resulting from solidification of the lunar magma ocean. And it's mostly consisting of plagioclase and anorthositic plagioclase, basically. Besides that, there is additional evidence for secondary lunar crustal suites. And the main suite that I'm going to talk about here is the magnesium suite. This is secondary crust. It's a very lithologically diverse suite of rocks. Its origins are somewhat enigmatic. We don't precisely know how it formed, but there are some ideas about it, of course. And it was likely produced by remelting of LMO cumulates. And there's an even more mysterious suite of rocks, and this is known as the alkali suite. It's also lithologically diverse. It's more felsic than the magnesium suite, and it's either produced also by remelting of LMO cumulates, notably including creep as well, or by fractional crystallization for magnesium suite magmas. And the origin of these crustal suites is all a little bit debated, as well as the ages are as well. And I would like to explain this in a slightly more detail using this diagram that is shown here. This is a plot that shows you the magnesium number in mafic silicates for rocks from each of these rock suites versus the anorthite content in plagioclase. So starting off with the FAS, the Verona Northocides, you see that they kind of form an array here towards high anorthite content in plagioclase. And this mineral chemistry is consistent with production of that FAS through crystallization of the lunar magma ocean. Now, the other two crustal rock suites cannot be produced from this LMO, from the FAS, sorry, and it's likely produced by remelting of the LMO. And you see that the trend, there's somewhat of a trend from the upper right to the lower left that may be a result of fractional crystallization. And you can also see that the various rocks that are associated with the magnesium suite have kind of different contents. The alkali suite plots here to the lower right. And then there's another ingredient that we can look at here, and this is the rare earth element patterns of these various suites of rocks. And this is shown in this chondrite normalized rare earth element plot. Let's start here on the bottom of that diagram. This is the pattern, kind of average pattern for the FAS. It is depleted in rare earth elements, but it shows a pronounced europium anomaly. And by contrast to that, creep-rich samples like this creep basalt, they are very enriched in rare earth elements, and they show a negative europium anomaly. So they're kind of complementary patterns, and that is in itself kind of geochemical evidence for the lunar magma ocean model. Now, the other two suites of rocks, the magnesium suite and alkaline suite, plot in between. So you kind of can create these suites of rocks if you combine Verona Northocide, values from Verona Northocides, with those from creep. So if you put that all together, you can kind of infer that the magnesium suite is derived from a combination of a mafic component, with high Mg numbers, very mafic, a plagioclase component that's high in anorthite, and an ore-creep component. And as a consequence, the magnesium suite and also the alkali suite must, at face value, have formed after the LMO cumulates. So after the FAS, the mafic cumulates, and ore-creep. So that's where things stand from a kind of geochemical and petrological point of view. Now, so again, the basic lunar evolution model predicts two stages of crust formation: primary FAS crust and secondary magnesium and alkali suite crust. And the question then is, can we observe this in the age determinations on these lunar crustal rock suites? And this can be tested by doing age determinations on these rocks. Well, this has been done for many years, for many decades. And here's the picture that we get. This is a diagram showing you kind of absolute age determinations on various lunar crustal samples for each of these crustal rock suites. And there are several observations to be made here. So first of all, for the FAS, for the anorthosites, you see that there's a very wide range of ages ranging between about 4.2 and 4.5 billion years. So that's very widespread, and that at face value would suggest that this magmatism occurred over some period of time. Then there's the magnesium suite, and this actually shows a very similar pattern. So the ages are also very widespread, and they're as old, they overlap the Verona anorthosite suite. Now for the alkali suite, we actually don't have very many ages, and that's in part because samples from the suite of rocks are very scarce, and it's very hard to date them. There are only maybe 1 or 2 rocks that have been successfully dated. But what we do have are detrital zircons from the lunar surface that do not occur within any petrologic context. And the histogram of these ages that have been mostly determined using uranium lead is shown here in the upper diagram. And you see that, again, for this suite of rocks, there's a very wide range of ages, but with a pronounced peak at about 4.35 billion years. And together, this range of ages also overlaps that of the other 2 suites of rocks. So looking at the ages that we have, this is all somewhat inconsistent with what I just told you from the geochemical stratigraphy of lunar samples. Now, this could mean that maybe our models are incorrect, maybe the lunar magma ocean model is incorrect, maybe our models for the formation of the magnesium suite are incorrect, and that we have to revise this. An alternative is that there are some issues with these ages. It could be that some of the ages are incorrect, that some of them actually are decades old, so maybe they were not well determined. It could be that they're misinterpreted, that some of them do not date igneous events, but metamorphic events, for example, as a result of impacts. It could also reflect the large uncertainties associated with some of the chronometers that we use. And all in all, I think it also maybe reflects the fact that we've only overall dated only very few samples successfully. There's only a limited number of samples that are useful for dating for age determinations from the lunar crust. So this is a bit of an issue, and what we would like to do here, or what is kind of our research agenda at this moment, and what we've also been working on over many years, is to reconstruct the history of crustal growth on the moon by determining more reliable ages and more precise ages for these suites of crustal rocks. And our approach to this question is kind of twofold. We would like to improve the precision by making use of the precision provided by the uranium lead system. And we would like to verify the accuracy of the ages by dating each sample using multiple chronometers. Okay. So as an aside, I would like to briefly explain a few things about the chronometers that I will be presenting about here. So first of all, the uranium lead system. This has been mostly applied to zircons, but it can also be applied to pyroxenes, for example. And it's essentially based on 2 decay chains. One that's based on the decay of 238 uranium to 206 lead, and the other based on the decay of 235 uranium to 207 lead. So that's very useful. We have 2 ways to determine ages using this system. And if you plot these ages against each other, you can construct Concordia diagrams like these, where the curved line shows you the line of equal age for the 2 decay chains. You can also combine these 2 decay systems to construct lead-lead ages. And that's very useful for dating old samples. Now, the other system that I would like to discuss is the samarium system. And in this case, we do not typically not date single minerals or whole rock samples, but we do construct mineral isochrons. So that involves a lot of mineral picking, different minerals that are contained within a rock sample, and this allows us to construct isochron diagrams. An example is shown here for the long-lived samarium neodymium system, where the isotopic ratio is plotted versus the samarium neodymium ratio of the individual minerals. And the slope of that line is proportional to age. Now, again, there's not one, but two decay chains. There's also a short-lived system that's based on the decay of 146 samarium to 142 neodymium. And that's also quite useful for interpreting the chronology. Now, the reason we're using two chronometers is that they each have advantages and disadvantages. The uranium-lead system provides highly precise absolute ages, but it's easily disturbed. The samarium neodymium system provides very robust ages, and as such is a reliable recorder of igneous events, but its precision is rather limited. But we can combine the two and kind of take advantage of both chronometers. And that's typically what we do. So we combine these two chronometers through the same crustal sample. Now, and how this is done is I'm not going to go into too much detail, but I would briefly like to highlight kind of the techniques that we use. So we typically take a sample, it may be a couple hundred milligrams up to a few grams in size. It is characterized using SEM, microprobe, and then part of the sample is we do mineral separations on that sample. So we get different fractions, and then these mineral fractions are dissolved in a clean lab, and we perform ion chromatography to purify the elements of interest. And then the samples are measured on a mass spectrometer using, in our case, typically using a TIMS, a thermal ionization mass spectrometer. And this is this is the instrument that we use both for samarium neodymium, rubidium strontium chronology, but also for uranium-lead ID TIMS chronology. The other technique that we've used is an in situ technique, and this is secondary ion mass spectrometry. And in this case, we use this for lead ages of some of the rocks that that we're looking at. And what we'd like to present here is kind of chronological results for 3 samples that we've studied over maybe the past 10 years. So it's kind of an ongoing effort. I would like to present some recent data, but also some data that is already in the literature and that has been obtained mostly by Lars and his group about a decade ago. And this includes FAS sample 60025, magnesium sweet sample 78238, and quartz monzodiorite classed, which is likely part of the alkali suite, from an impact breccia, or a breccia known as 15405. Okay, so I'd like to go through the results obtained for each of these samples in the next few slides. And let's start off with FAS sample 60025. And this is a sample from the Apollo 16 landing site. A problem when dating vorononortisite samples is that they're typically almost monomineralic. So they often have very low abundances of mafic silicates, but by definition, of course. The advantage of 60025 is that it's a unique pyroxene-rich sample with fairly large pyroxene crystals that occur in a relatively high abundance. And this makes it datable using not only the samarium neodymium system, but also the lead-lead system. And that's exactly what has been done about 10 years ago, and that was done in collaboration with Jim Connolly at the University of Copenhagen. He also obtained a lead-lead age for this sample. And the results for that are shown here. This is a diagram, a kind of a lead-lead diagram, where the radiogenic isotope ratio 207 over 206 lead is plotted versus the common lead over radiogenic ratio. And what you do is you take a very pure pyroxene fraction, you do multiple washes of that sample using various reagents. And then the idea is that if you wash it long enough, you get closer and closer towards the purely radiogenic composition, and that's defined by the intercept here. And that intercept value is proportional to age. And that doesn't work with every sample, but with this sample it worked remarkably well. And a very precise age was obtained of about 4.36 billion years, plus or minus only 2 million years. So that's exceedingly precise. Now, to corroborate the accuracy of this age, samarium neodymium ages were obtained as well, both using the long-lived and the short-lived system. And I'm showing you the the results for the long-lived system here, an age of 4.37 billion years was obtained, and this is concordant with the lead-lead age. So this gives us a lot of confidence that this age is accurate. And in fact, we have 3 concordant ages for the single sample, resulting then in a weighted mean age of 4359 plus or minus 3 million years. So if we believe that this sample is representative for the FAS, for the Verona Northside Suite crust at large or as a whole, then this would mean that this crust formed at 4.36 billion years. All right, so let's move on to the magnesium suite. So magnesium suite samples 78 through 238, and several well-dated magnesium suite samples derived from the Apollo 17 landing site. This sample is a shock norite sample collected at Station 8, to the upper right of this diagram here on this map. And this sample, well, it's a typical norite, and the good thing is that it also contains some mostly badalites, but also some zircons that can potentially be dated using lead-lead SIMS chronometry. They're small, but they're datable using in situ methods. But I should also mention that this is a very well dated sample. There are several studies in the literature, and many of these studies yield a 4.33 billion year age. So this is kind of what we already know. But more recently, Ming Chang obtained some in situ ages for this sample at UCLA, and the results are plotted here. So these are lead-lead ages for this sample, and the mean age that he obtained was 4.333 plus or minus 3.9 billion years. So again, very precise, right? It's an uncertainty of only 4 million years. Now, and if you compare this to literature data, there is, for example, a study by Edmondson et al. Lars was closely involved with that work. And it turns out that the samarium-neodymium chronometry of that sample is concordant again with the lead-lead chronometry. Again, an age of 4.334 billion years. So that's very good. And if we believe that this sample is representative of the magnesium suite, this would mean that the magnesium suite formed or crystallized at 4.335 billion years. Yeah. Now, in the next part of the talk, I would like to kind of take a step aside and talk a little bit about the development of our uranium lead capability here at Lawrence Livermore National Lab. And this is something I've been working on quite a bit over the last 2 years. And in an effort to kind of add this chronologic system to our repertoire of systems that we already apply here at the lab. And one of the principal challenges when using this system is that it's a very blank sensitive system. And that is because the air that we all breathe has a high abundance of lead. It's about 100 nanograms per cubic meter of lead that is in the air. So you need very clean air when you want to apply this system accurately using ID-TIMS. And I should emphasize, we're setting up the ID-TIMS method, so solution isotope dilution uranium lead work. Now, so one of the first things we assessed and kind of had to kind of do some improvements about is the loading blanks associated with the TIMS method that we apply. And they're plotted here. So this is the amount of common lead plotted essentially over time. So this work was started by Kyle Semperton here at Lawrence Livermore Lab in 2020. He then left and I took over some of that effort. And you see that progressively the loading blanks decreased over time. And now we're here in 2024 and they're essentially consistently below 100 femtograms. And a notable change happened when we changed the filters of one of our hoods. It turned out that they were very old, and after changing them, the loading blanks dramatically improved. So after that was improved, we could actually start setting up the method, and that involves chemical abrasion of minerals, and it involves chemistry, and it involves mass spectrometry. And it is in fact, if you want to apply it to zircons, it's quite convoluted. And happens in multiple stages. So what we typically do first is an annealing step involving annealing in a muffle oven at 900 degrees Celsius for over 60 hours. And then the zircons that we're interested in are subjected to various leaching steps and washes and abrasion steps. And part of the reason that this is necessary, that we have to remove common lead from the zircon itself, from radiation damaged zones. Another reason is that a lot of the zircons that we are interested in from lunar crustal samples occur closely interspersed with silicate minerals. So we had to dissolve these mineral phases kind of around the zircon to get an accurate age for the zircon itself. So what we typically do is a cold leach using various reagents. Then we do 2 chemical abrasion steps in an oven, in a par bomb. And then the residue is spiked using a tracer, a uranium lead spike. And then this residue fraction is dissolved in the par bomb at high temperature for 48 to 60 hours. And after that is done, the uranium and lead are purified using anion exchange chromatography, and then the isotopes are measured using the Triton TIMS here at the lab. So here are some results that we obtained for reference zircons. These are Tomora zircons and these are results obtained over the last maybe 1.5 years here at the lab. The mean ages are shown here both to the left and to the right. Left is a Concordia diagram, and the age obtained is highly precise. It's 417 plus or minus 0.05 million years. And this value that we obtained is in excellent agreement with kind of the reference value from the literature. So that gives us a lot of confidence that our method yields accurate ages. A lead age here to the right is concordant with the uranium lead ages and is also very precise. And the total blank is at the moment less than 1 picogram. That can still be improved quite a bit, but at this point it is good enough for what we want to do using lunar samples. So, and this is what I would like to discuss next. So the next sample we studied is a quartz monzondiorite class from 15405. And this is thought to belong to the alkali suite. It was collected during the Apollo 15 mission. And it's a rather felsic class. It consists of plagioclase, pyroxene. You can see the false color image here. It consists of K feldspar quartz. And notably also, it has a fairly high abundance of zircons. Not as high as we thought it would have, as was reported in the literature, but we were able to separate some zircons from this rock. That was no easy task. We actually used the mineral fractions that we used also for some of the isochron work to do kind of mineral separates for zircons. And we essentially had to use the SEM to find these zircons. And we had to scan for high zirconium concentrations, for example. And we only found about, well, I think 10 to 15 useful zircons and that we could date using this rock. And they're still fairly small. They're about 50 to 80 microns in diameter. But fortunately, using the new technique that we developed, we could determine uranium lead ages for a few zircons from this sample so far, and more work is in progress. So here are the first results that we obtained. This is again a Concordia diagram showing you the data. You see that there are data for several points here, some leachate fractions, some residue fractions, and most of the zircons plot fairly close, or some of the zircons plot very close to the Concordia, and they yield a very precise age of 4.337 plus or minus 1 million years. So very precisely determined. You can also see that some of these fractions plot along a discordia line, so there is some evidence for a secondary disturbance. Nevertheless, there are some zircons that actually yield undisturbed ages. We also obtained several mineral isochrons for this class, both using the long-lived and short-lived samarium neodymium systems, and these chronometers yield ages that are concordant with those obtained using the uranium lead system. So that's great. So we have a weighted average age for this class of now 4.337 plus or minus 1 million years. And this is consistent with, but slightly more precise than prior SIMS ages on this QMD class. Now let's put this all together. So again, this is the diagram I showed you at the beginning. These are the literature data. Again, previous work revealed a very large range of overlapping ages for all crustal rock suites. And even if all these ages were correct, there's still an issue that some of these chronometers do not have the accuracy to resolve small-scale variations, because that's exactly what we're looking at. So if I plot the data obtained for the 3 samples I'm discussing today in here, you see that they define a very narrow range of ages. So the chronology in essence is very strongly compressed between 4.33 and 4.36 billion years. So based on the existing chronology, you would never have drawn the conclusion, or you would never have been able to predict that it would be so closely spaced together. Now the question then is a question of representation. Is this range of ages representative for these crustal rock suites, or or in reality do they not represent these crustal rock suites, and are they in fact produced over a more extended period of time? If these ages are representative, this must mean that the wide range of ages partly reflect erroneous age determinations, erroneous interpretations, or secondary resetting and poorer precision. So I would like to briefly highlight a few things regarding how representative these samples are. And for the Verona Northicides, in fact, I think we can make a case that this is representative for the Verona Northicide suite at large, because we don't only have ages for sample 6025, but also for a few other FAS samples that have not been as precisely dated as 60025, but they all plot on a common whole rock and mineral isochron yielding an age of 4.37 billion years. So that's pretty consistent with the precise age obtained for 60025. For the magnesium suite, we can make a similar case. So we don't only have high precision ages for 78238, but we also have samarium neodymium ages for a whole bunch of other magnesium suite rocks. And they also collectively produce a whole rock isochron with an age of 4.348 billion years, again concordant with that high precision age. For the alkali suite, this is a lot harder because we haven't dated as many samples, and in particular, we don't have many isochron studies for this suite of rocks. But what we do have is the histogram for the detrital circles. And as a matter of fact, the QMD class, in fact, the age for that plots overlaps with the peak of the detrital zircon ages. So if you believe the detrital zircons to also be a result of alkaline suite magmatism, then for which you can make a case based on this concordance, then this may also be reflecting of alkaline suite magmatism at large. And what I should emphasize here too is that the QMD class, in fact, very clearly is an igneous sample. So this may clearly indicate that this dates an igneous event. So based on that, I would argue that it's not too unreasonable to extrapolate these high precision ages determined on only 3 samples to the lunar crustal rock suites. So I know that, of course, this is that there's definitely a sense of extrapolating in here, and it would be highly beneficial to obtain additional ages for each of these crustal rock suites. But let's for a moment assume that these ages are representative, and let's have a look at the picture that then emerges. And that is shown here. So we have 3 ages, and based on the age for 60025, we would say that FAS magmatism occurred at 4.36 billion years. Magnesium suite magmatism occurred at 4.334 billion years, and alkali suite magmatism occurred at 4.337 billion years. And based on that, you could argue that in kind of looking at this high resolution chronology, that FAS magmatism occurred 25 million years before magnesium suite and alkali suite magmatism. And that, in fact, is consistent with what I said at the very beginning. It's consistent with the prediction from LMO models and the geochemical stratigraphy of the lunar crust. Another important observation is that magnesium sweet magmatism apparently is contemporaneous within just a few million years with an uncertainty of alkali sweet magmatism. Another extrapolation I would like to make, and that's a slight aside, is regarding the ages of LMO cumulates. So based on this, we would argue that the FAS crystallized at 4.36 billion years. And as it turns out, this age is in fact concordant with a samarium-neodymium whole rock isochron age determined for Mare basalts. And this is in fact an age dating the formation of the Mare basalt sword regions based on the short-lived SMND system. And these ages are concordant. And that's, in fact, I think this is a very important observation and an important set of data, because what it shows is that there was isotopic equilibrium between mafic and felsic LMO cumulates at 4.37 billion years. So regardless of what you believe about the age of the moon and the exact time scale, for example, of creep formation, I think this is an important observation that cannot be ignored. Now, let's have a look at some implications. Well, first of all, let's discuss the relationship between the magnesium suite and the alkali suite, because we can say something about this using the new results. And there are several key observations to be made here. The first of all is kind of what I already alluded to, is that based on these high precision ages, it becomes clear that the magnesium suite and alkali suite formed contemporaneously within a very, very short period of time of just a few million years. So 4.335 billion years. Now we can not only look at the chronology using some of these systems, but we can also look kind of at the protolith, at the source from which these rocks are derived. And the samarium-neodymium system is particularly useful for this. And so essentially this information comes from the samarium-neodymium isochrons. So the isochrons, in other words, don't only tell you something about the age of the sample, but the initials of the isochron also tell you something about the source the sample derived from. And as it turns out, the initial epsilon 143 values, so chondrite normalized values, for both of these rocks are indistinguishable. And that is consistent with the fact that the sources of these rocks derived from or that these sources had very similar time average samarium-neodymium ratios. So very, very similar sources from at least a rare earth element perspective. And I think that's a very important observation to make here. Now we can take this a little bit further, and this is a little bit more arm waving, but we can also interpret this in the context of the evolution of creep. And that is based on the idea that these rocks ultimately, in part, derive from creep-rich sources, and in particular the rare earth element budget of these rocks that samarium and neodymium are part of is likely governed by creep. So you can ask yourself the question, when did these rocks derive from a creep source? And this is consistent in general with the evolution of creep. And to look at that, I included this diagram here. This is a diagram of the initial 143 neodymium versus age. It's a TI diagram. And essentially, the horizontal line here is the evolution of chondrites. And at some point, the creep reservoir, in the context of LMO crystallization, would have separated from a chondritic reservoir. And then at some point later, the sources of the QMD and the magnesium suite would have formed. And it turns out that the ages alongside the initial 143 neodymium values plot on that creep evolution line. And there's quite a lot of slop here. There is quite a lot of uncertainty, of course, in the epsilon 143 neodymium value. And the other aspect to this is that the evolution of creep is quite debated, especially now. There's debate as to when creep formed. It may have been around 4.36. Some argue even much earlier. But regardless of which interpretation is taken to be true, overall, the sources of these rocks are consistent with derivation from creep. And this implies that QMD and the alkali suite and the magnesium suite are petrogenetically linked and produced by a common mechanism. So in other words, regardless of you need a formation mechanism that can simultaneously explain the magnesium suite and the alkali suite, and for that matter also the formation of the source of the trityl zircons, if you believe these to be linked to the QMD class. Now finally, I would like to briefly discuss the interpretation of this 4.335 billion year age, so essentially the formation time that we now infer to be for the magnesium suite and alkali suite. And in essence, because these rocks are mostly igneous, and we believe these ages to reflect igneous events, this must require a major igneous event on the lunar near side at that time. Now the question is how you do that, and it's about 25 million years later after formation of the Verona Norte-side suite. And what you need is a heating mechanism at the time that causes widespread melting. And there are several mechanisms for this. There are probably quite a few that I'm not considering here, but I'd like to consider 3 possible mechanisms. And the first is, and this is something that has been proposed already about 30 years ago or longer, is that a large impact, maybe SPA, as has recently been proposed, cause widespread melting of the lunar near side, or maybe even at SPA, and this would need to have been a very large remelting event, causing melting of the crust down to several tens of kilometers, because for some of these samples we believe that they derive from that deep. That's a possibility. It's been proposed. I think it could explain the data. But I've not, I should say, seen exceptionally convincing evidence that it need to have been an impact. Another possibility is that it is a result of density-driven overturn of the lunar melting in the aftermath of lunar magma ocean differentiation. And it could be that some cumulate layers or some melts rose to the kind of the top of the mantle, to the base of the crust, and that would have led to adiabatic remelting of some of these cumulate layers. And alongside, and if you combine that with the chemistry in that region, this could provide a heating mechanism as well. Maybe not so unlikely, and I kind of like this idea because it would be a natural consequence, essentially, of LMO differentiation, and especially given that this chronology is now so kind of constricted to a relatively narrow time window, the idea that this would have happened about 25 million years after differentiation of the lunar magma ocean is not so unthinkable. Another possibility that's, I think, also been proposed is that tidal heating of the moon after its formation was responsible for the secondary pulse of magmatism. That is a possibility. I'm not sure how likely it is. And for one thing, you would have to explain that this only happened once and not over an extended period of time. So this tidal heating mechanism would only need to have occurred kind of at that time and not much later than that. And finally, it is possible that combination of these processes was responsible for this. It may not be one or the other. It could, for example, be that a large impact resulted or spurred overturn of the lunar mantle, for example. Okay, well, to finish this up, some implications, conclusions, inferences. The magnesium suite and alkali suite have narrowly defined and concordant 4.335 billion year ages, implying a common formation mechanism. I think that's a first order conclusion we can draw from these data. And an implication from that is that these ages overlap with a peak in the trityl zircon ages. And this may imply that the younger the trityl zircon ages determined mostly record impacts or impact metamorphism, but it could also mean maybe that we have an as yet unsampled suite of igneous rocks that are circumbearing on the moon as well. Magmatism associated with the formation of the secondary suites of rocks, as well as the trityl zircons, occurred only 25 million years after the formation of mafic and felsic LMO cumulates. which happened at 4.37 billion years, and as such, the chronology is strongly compressed. So what we need to do is to develop models to account for the near contemporaneous production of primordial crust in a global cooling regime. So after kind of initial formation of the moon and after following cooling of the magma ocean versus secondary crust that was likely produced in a heating regime. So that has to somehow be constrained. And regardless of all of this, and also to make sure these ages that I presented are representative, we need new high-precision ages for constrained using multiple chronometers, including the uranium lead system, but also the samarium neodymium system on reliable crustal samples. Thank you very much.
Thank you so much, Thomas. And then I'll go ahead and open the floor up to questions. I think we had a question in the chat for a slide that was a little while ago. I think it was in the middle of it, and it was asking about what is the significance of the 0.8 picogram line in one of your charts.
0.8 picogram?
Yeah, it was a chart. I remember it had the dash line. Which one was it?
One with the blanks?
Yeah, the blanks. Yeah. Yeah, I think.
That one.
Yeah, that's the one.
Yeah.
Oh, that's a good question. I think that is a limit I set myself as a goal, and I think I decided that at about 0.8 picograms, if the average blank was about 0.8 picograms, then we would be good with respect to accuracy, and the blank corrections would be sufficiently small that we can obtain accurate ages.
Okay, thank you, Thomas. Any questions from us here in the audience?
You can take them from online. I've got the questions, but do them online first.
Okay, we'll do the ones online first then.
I have a somewhat technical question. This is Justin.
Hi, Justin. Hi.
Hey, yeah, great talk, like I said before. So and this may be just a function of the one study that you showed, but in the uranium lead chronology, this is the solution work, you showed the pherone anorthosite that had pyroxene in it, and made a very compelling case that this was a somewhat unique sample that was really ideal for that type of chronology because it had the pyroxene. And then you showed the data. These were, I think, Jim Conley's data, but the data that were for the pyroxene and the leaches of the pyroxene. But you didn't include any of the feldspar. Now I know that pyroxene or lead in pyroxene is different than lead in feldspar, but it's not like depleted in feldspar, and you have a ton of feldspar, but you didn't show the feldspar data. Is there a reason why?
I think the most well-defined ages were obtained for pyroxene fractions, and the uranium lead systematics are most well behaved for that. Maybe Lars can speak to this better because he was directly involved with that study at the time. I'm not sure if you want to comment on that, Lars.
Sure. Feldspars are not good recorders of the lead compositions because they're very easily reset by impacts. So what we found is that the lead in feldspar is very mobile, and the lead in the pyroxene is less mobile. So specifically what we found was that the lead that we analyzed from the feldspars had very high 7:6 ratios, indicative of contamination from regolith. And so that just basically reflects the recrystallization of the feldspars during the secondary heating events, of which these rocks have seen numerous episodes of. But the point to note here is that we had 3 chronometers that all gave concordant ages, and so that's why we had confidence. I personally wouldn't trust the uranium lead age on its own ever.
Okay, thanks. Yeah, I feel like, and I know we've talked about this a number of times, but I feel like when you have 3 chronometers that are composed of the same phases, then that's a little bit more fair argument that those are 3 chronometers. Whereas when you have one that's essentially one phase and then another that's of the other phases, there's nuance there. But I very much appreciate the fact that those are really nice data, and I won't argue with that. Thanks.
Thank you, Justin. Qingzhu, I think you have a question.
Yes, I do. Thomas, that's a great talk. Really appreciate it, listening to it. So I have 2 sort of straightforward question. One is when in this context that you are presenting of these ages, when is a moon forms and what happens between the moon formation until 4.3 is something that I always wondered. And then the second is there are quite a few zircon ages, lunar zircon ages pointing to around 4.4-ish. What are they? What do they represent? So these 2 questions, I would like to hear your opinion about it.
Okay, well, that's a great question, and I know that that's very much a topic of debate. It is, of course, not really the topic of what I discussed here, so I'm going to extrapolate a little bit.
All right.
And it depends on kind of what you believe, which ages you would like to believe. And there is, and it's somewhat related to the slide I showed you a few slides back, where I showed you the SMND isochron for mafic cumulates of the lunar magma ocean for the Mare basalt storage regions, and the overlap with the Verona northosites. If you take that at face value, then you would have to conclude that the lunar magma ocean, I think that's pretty compelling evidence for lunar magma ocean differentiation at that time. So that would be about 4.37 billion years around that time. I know that there are also older zircon ages. If you believe these to be correct, and reflecting of igneous events on the moon, then we end up with a little bit of a problem, because to form such sources with that source enriched sources that would have crystallized zircons, differentiation would have even had to start earlier. So there is a bit of a disconnect between these 2, and I'm currently leaning a little bit towards the younger ages, so towards maybe 4.38 billion year age. But it's a topic that requires further investigation, and in particular the meaning of these old zircon ages. Of course, the creep model age also comes into play here, and that's debated as well. And that's another topic we can talk about that for quite some time. But maybe that age is not as reliable any longer, because it is a model age, right? So there are underlying assumptions, and it's reliant on the idea that creep is derived from a reservoir with chondritic samarium or lutetium hafnium. So that's what I would say to this at this point. Maybe one thing to add, that the age of the moon itself, that's an event that is very hard to date in itself. So you can only infer it and extrapolate well-dated events that are younger than that, right? So something like magma ocean solidification or crystallization is a geologic event you can date. Anything before that requires assumptions regarding, for example, thermal models or model ages. So they're inherently less certain.
If I can interject one thought here. The problem that we're facing in the chronology realm is we have very few dates. And so what we're trying to do is we're trying to put together a picture using just, really, 5 or 6 ages. And that's fraught with a lot of uncertainty. And the ages don't agree. And so there's right ages and there's wrong ages. And the other part, and so picking those is difficult. The other part that I would argue is that there's another component that's largely been ignored by all of us, and that is that we need to put this into the context of the broader petrology and geochemistry of the moon. And so there's some constraints placed on that Thomas started off showing. And if you want to use some of these ages, you have to abandon a lot of those ideas, like having a magma ocean or having a giant impact and things like that. And so I think it's the jury's a bit out still. You know, we know it has to be after 4.5 because we don't have live tungsten or live hafnium 182. But after that, I think, you know, there's cases to be made on all sides of this, and it really comes down to what you're willing to throw out and what you're willing to accept and keep.
Well, thank you, Lars, for that. We also have another question from Justin. Would a primordial / primitive lid produce zircon that could be xenocrystal prior to lunar magma ocean differentiation?
Yeah, that's hard to, that would be very speculative. That's hard to constrain, I think. Maybe, but you need, of course, a high degree of magmatic differentiation and fractional crystallization to produce rocks that or magmas that crystallize zircons. But yeah, that's something. I mean, things like that are something that could be explored, of course. That could be a way out to explain the older zircon ages.
Yeah, I think that it's a reasonable way to explain them if you accept them. I mean, the alternative is that they're from meteorites or some foreign body, right? But you know, a quenched lid happens. You have to have cooling at the surface of the molten body, and you know, if it's not differentiating, if your entire, I mean, of the entire planet, if it's just the, you know, the quench at the surface, who knows what, you know, type of composition you can produce in that sort of quenched scenario. And then once the zircon are formed, you know, they're pretty robust, like we know on Earth. So, you know, obviously, yes, it is speculative, but I feel more comfortable coming up with a useful model to test rather than throwing out data that I think are, you know, have robust ages that are hard to throw out. And they're not necessarily the same as a model age, if that makes any sense.
Yeah, I agree. I agree with that.
Chip, I think you had a question, or
Yeah, I had a quick question. You know, one of the interpretations of your 2 data points is that the magnesium sweet, alkali sweet style of magmatism occurred over a fairly narrow period of time. And that was quickly followed by Maury magmatism that may have started as early as 4.2 GA. Also, you have some alkali sweet or evolved lithologies that are clearly younger than that period of time with some of these felsic domes. What do you think the transition is between the processes that form the magnesium sweet, alkali sweet, and then the following Maury magmatism?
Yeah, that's a great question, and I think what is important here is the fact, the observation now from the chronology, that it's very close, kind of closely spaced in time, and that these ages are all for the magnesium suite, for the alkali suite, for the many of the detrital zircons, are all around between, say, 4.330 and 4.337 billion years. So a time interval of only a few million years. And that seems to me that is a one-off event, a single magmatic pulse that was relatively widespread. So you need kind of a one-off event, a one-off heating mechanism for that as well. For example, such as overturn or maybe a large impact. I think that the other magmatism that was more prolonged that you're talking about, like that pre-basaltic magmatism, for example, that was maybe magmatism that occurred at a somewhat lower rate, and as the consequence of that would be is that the heating mechanism for that is also different. That maybe there were smaller bodies of magma in the crust or near the base of the crust that produced smaller volumes of melt, and maybe things like radioactive heating or from elements that are radioactive was more important in that style of magmatism. That's what I would surmise. But
Thank you so much, Thomas. And unfortunately, we are out of time. So again, Thomas, thank you so much.